This video shows the simulations and experimental results that validate the efficacy of our collision cone control barrier function, C3BF. Using the acceleration-controlled Unicycle Model, Python simulations in different scenarios were performed to get various obstacle avoidance behaviors like turning, braking, reversing, and overtaking. We also validated our algorithm on pybulate simulations for similar scenarios. Differential drive turtle robots were used as the ego vehicle to realize the Unicycle model. Straight-line reference trajectory was considered for the ego vehicle to track using PD control, which can be replaced with any state-of-the-art path planning algorithms in practical scenarios. For the static obstacle case, a rigid cylindrical object was placed on the robot's path. We can see that the robot avoids the obstacle and again comes back to its desired straight-line course. For the moving obstacle case, similar turtle robots were placed on the ego vehicle's path with different heading directions. We can see that safety is always ensured with overtaking and reversing behavior. For practical testing, we incorporated the C3BF with Copernicus mobile robot. We can see that, initially, the robot follows the reference trajectory, and as the obstacle comes inside the perception boundary of the sensors, the QP actively starts modifying the reference control inputs to avoid it. As soon as the obstacle is avoided, the QP again becomes inactive. This comparison shows the effectiveness of C3BF on a spline reference trajectory with a static obstacle on it. After smoothly avoiding the block, the robot again tracks the spline trajectory using the reference controllers. For testing our algorithm in a dynamic environment setting, we used another robot, Volta, to act as a moving obstacle. We tried different scenarios by changing the obstacle's pose and velocity, and interestingly we got different collision avoidance behaviors of Copernicus, like reversing, turning, and overtaking. Additional experiments with reference spline trajectory were also conducted, including multiple stationary, same-direction moving, and perpendicularly moving obstacles. Notice that even with a slight change in the initial conditions, obstacles were always avoided with different maneuvers. Moreover, braking was also observed in the scenario with multiple obstacles where an optimum circumnavigating path is difficult. For the acceleration-controlled bicycle model, Python simulations were first performed without reference control in different scenarios. And then with a Stanley trajectory tracking reference controller on a spline path with an elliptical static obstacle, as shown. We can see that the agent avoids the obstacle by circumnavigating. To further test C3BF's effectiveness in a real-like scenario, numerical simulations were performed using the CVXOPT library on the Carla simulator with moving obstacles such as pedestrians and cars. Information about the obstacle was programmatically retrieved from the Carla server. A virtual perception boundary was incorporated to accommodate the range of perception sensors on real self-driving cars. Various situations were tested by changing the Carla environment, as shown. The side figure graphically illustrates the formation of collision cones on the obstacles as they are detected, and then the C3BF QP alters the reference control inputs to take out the ego vehicle from the course of the collision, exponentially. Note that the environment is just for visual purposes, without considering driving or traffic rules. Notice that whenever an optimal circumnavigating path is unavailable, like in the bottom right case, the ego vehicle smoothly brakes, thus ensuring safety. Before testing our C3BF for the bicycle model on hardware, we validated it on pybulate simulations. F1 car, with rear-wheel drive and Ackerman steering, was used as the ego vehicle to realize the bicycle model. Stanley controller was used for straight-line reference trajectory tracking, which can be replaced with any state-of-the-art path planning or trajectory tracking algorithm in practical scenarios. Both static and moving obstacle setups were simulated. For the moving obstacle case, a similar F1 car was placed on the ego vehicle's path with different heading directions. We can see that safety is always ensured with unique behaviors. In hardware experiments, a FOCAS robot car with rear-wheel drive and Ackerman steering was used as the ego vehicle. Turtle robots were used as the static and moving obstacles. States of our ego vehicle and obstacles are measured using the phase space motion capture system. Just like Pybulate and Python simulations, obstacles were always avoided irrespective of initial conditions with different behaviors, as shown. In conclusion, this video compiles the simulation and hardware results showing the working of our C3BF filter to avoid static and dynamic obstacles in real time with both unicycle and bicycle models. Our future work will include combining C3BF with existing state-of-the-art path planning algorithms. We will test it on a full-scale self-driving car in real-life scenarios and quantitatively analyze the safety enhancement due to the C3BF filter. For more technical details, please follow our manuscript. Thank you.